In example 13.6, we're going to put a 1,000 kilogram satellite into a circular orbit that's 300 kilometers above the surface of the Earth. We wish to calculate the speed, period, and radial acceleration that this satellite must have in the orbit. Then we're going to calculate how much work was needed to put the satellite in orbit and how much additional work would be required for the satellite to completely escape the Earth. So let's begin with the equations that we'll need. The main one is equation 13.10 that tells us the speed of a satellite in a circular orbit of radius r. And here's the equation for the radial acceleration. The period of the satellite, of course, is 2 pi r over the speed. First thing we need to do is calculate the radius of the orbit. The Earth's radius is this, and we're this far above the Earth, and so the total radius, the total distance from the satellite to the center of the Earth is 6680 kilometers. We need to convert that into meters. Plugging that into this equation, we get 7,720 meters per second. The period is the distance traveled in one cycle of the orbit, which is 2 pi r, divided by the speed of the satellite. And that turns out to be about 90 minutes. And the radial acceleration will be the speed squared over r, which is 8.92 meters per second squared. Now let's turn our attention to the work needed to put the satellite in orbit. We're going to use conservation of energy. In the final position, the satellite has a total mechanical energy we're going to call E2. The initial position is on the launch pad and has a total mechanical energy E1. Let's start with this one. We're going to use equation 13.13, which states that the total mechanical energy of a satellite in an orbit of radius r is given by this expression. We can put in the numbers. This comes out to be minus 3 times 10 to the 10 joules. The initial mechanical energy is given here. We're going to assume that the satellite's at rest on the launch pad, and so all I have is the potential energy of gravity, and I put in the numbers. And this becomes minus 6.24 times 10 to the 10 joules. Now the work required would be just the difference in these two energies, and that turns out to be a positive as expected, 3.26 times 10 to the 10 joules. And finally, we'd like to calculate how much additional energy would be needed to get the satellite out to infinity. Well, at infinity, the total mechanical energy of the satellite is given by this equation, will be 0. So in this orbit, the satellite has this much energy, mechanical energy, and I got to get this to 0. So I'm going to have to add to the satellite exactly this amount of energy. So I need to add 2.98 times 10 to the 10 joules. And finally, if we go back and look at this acceleration, we notice that it's not too far from 9.8 meters per second squared. And in fact, if I were to calculate the gravitational force on the satellite at this radius and divide that force by the mass of the satellite, I must get this number. And this ends example 13.6.